In this lecture on overturning, we're first going to examine the overturning about the toe of the tower assembly. In the same way we evaluated the entire abutment for overturning in our Tier 1 checks for the basic design course, we have an overturning moment from the horizontal cable forces shown in red and a restorative moment from the self-weight and vertical cable forces shown in blue. These forces do not change from our basic analysis. However, we will move the point in which we evaluate these forces upward to the toe of the tower assembly, which I've shown here in white. And I'll give you a moment to check out this diagram. There's a lot of information. A lot of this information we discussed in the introduction and loads portion of this module, but I just want to reiterate it here with a little bit more detail. I've also added some material properties here, and you can cross-reference this with the tower details in order to get your bearings on what is what. So we have our masonry formwork, our structural concrete. We have the handrail cable and the location of that handrail cable force is going to be at the center line, and that is going to be offset from the tower center of mass by that tower offset value. So we have two center lines here. We have a bridge center line that is going to be consistent between the two tower columns where the cable sits, and we have the tower center line, which is going to refer to the tower center of mass, where that value of P tower, the weight of the tower, acts through. And this check goes hand in hand with the check for tower eccentricity. So as you set this up and work on your actual site, you may notice that both of these checks should be closely related and will fail or pass under similar conditions. And that is the next check we'll talk about after this module. But for some theory, the main idea here with the tower overturning check is we're checking the tower assembly as a rigid body. Assuming the assembly is a solid block, a passing tower overturning check will tell us that the entire tower base is in compression. Because there is no positive tension connection between the tower assembly and the tiers below, this is necessary. Now, we can come up with a factor of safety for this check, but that factor of safety still isn't telling us much, that it is just going to be a pass-fail, or it's going to be our factor of safety against that pass-fail. And I've drawn the short indicative diagram here showing the toe of the tower, the forces on the tower, and what would happen in a overturning situation or a not passing situation. There is going to be tension on the side opposite the toe of the tower. Now, as you may remember for the lecture on loading, the overturning moment can be taken as the handrail and walkway cable forces, horizontal component, multiplied by their respective height from the toe of the tower. Sorry, I missed one more piece I wanted to talk about. Beyond just this rigid body overturning, we can then look at the stresses at the toe of the tower and how the force flows into the walkway hump below. And like I said before, we don't want to have any tension. So a passing check is going to look like this in green. And compression, we're going to have larger compressive stress towards that toe of the tower. It's going to be offset because, as you can imagine, there is still going to be some sort of tensile force here on this portion of the tower, and that's going to reduce our compression for a certain length. And because there is a compressive force on this side, it's going to increase our compressive stress on closer to the toe of the tower. And a not passing check would look like this on the right, where we do have tension on a portion of toe of the tower. In this case, we would need some positive connection from the tower into the tiers that is carrying the load into the tiers and mitigating it there. Now, as I was saying before, the overturning moment can be taken as the handrail and walkway cable forces horizontal component multiplied times the respective heights from the toe of the tower. So we have our 2 times h tower times ph hand plus h walk times ph walk. So our 2 horizontal forces multiplied by their heights. And the restorative moment comes from the total weight of the tower in vertical forces multiplied by their distance from the tower toe. And don't forget about the tower offset for cable forces. We can write them out in terms of the forces you already know and have calculated from previous analyses, which are the ph hand, ph walk, PV walk, and PV hand. And that here, our restorative moment, we have the 2 times our PV hand plus PV walk multiplied by that x distance, that x cable, which is going to be this x distance here, and the weight of a tower times that x tower, which is going to be that x distance here, but the difference here is just the offset. And finally, we check our restorative moment is greater than the overturning moment with a factor of safety of 1.5.